Okay, so next up we're happy to have Ben Zhu, who's going to tell us about W1 plus infinity algebra with a cosmological constant. Take it away, Ben.
Thank you. Thanks for the opportunity to speak. I'm going to talk about a paper from last year with Tom Taylor about W1 plus infinity algebra with a cosmological constant. Okay. Thanks. So here's the outline of my talk. I will briefly talk about some introduction about the ideas of celestial holography and celestial amplitudes, as Laura and Tim already gave a nice review of it, so I'll be brief about this part. And then I'm going to show you how the W1 plus infinity algebra was derived in the flat space case, and what has to do with the so-called celestial OPE. And from there, you can extract this algebra. And then I will talk about our main results, which is the W1 plus infinity algebra with a cosmological constant. I will talk about the motivation and the basic idea how we got it. So the idea of celestial holography is that the S metric, which is the observable of asymptotically flat space, might be described by a tilted celestial CFT living on the celestial sphere. We get some hints from the study of asymptotic symmetries. It has been shown that the conformal symmetry on the celestial sphere gets locally enhanced to via solar symmetries on the celestial sphere. So this is sort of like the first hint of there might be a putative CFT living there. And the idea is that we want to take the so-called bottom-up approach from which we can know something about the putative CFT from the transfer basis of scalar amplitudes. So the idea is to deduce some universal property of this putative celestial CFT from some known properties of scalar amplitudes in 4 dimensions. So as you already seen in Laura's talk, it's quite useful to do a transfer basis for the scalar amplitudes. So the usual way we parameterize the line momenta is in these ways. And then it turns out that we can do a Bernoulli transform with respect to the light cone energies. And this transfer basis basically makes the conformal properties on the celestial sphere manifest. And this is done for the scalar plane wave, and it can be done for the other particles involving, including spins. So the prescription is that we start from the scalar amplitudes written in these variables, and we do a Bernoulli transform with respect to all the light cone energies. And the results we get is the so-called celestial amplitudes. And you can check that this celestial amplitude does behave like correlators on the celestial sphere with conformal dimensions associated with each particles. So perhaps the most important thing in the given CFT is to know some CFT data which involves the OP operator product expansions. So a very natural question would be, how do we get the celestial OP expansions? And it turns out that this is really natural from the kinematic point of view, where we take, if we want to take 2 points on the celestial sphere to be close, it corresponds to taking 2 momentum to be collinear in 4 dimensions for massless particle, of course. And it turns out that the collinear splitting behavior for example, for gluons is universal for tree level, which is given by this simple form. And then once we've done the Bernoulli transform of these collinear splitting functions, we end up getting beta functions for the celestial OPE. Okay, so you can do this thing for the graviton collinear splitting as well, and we got this celestial OPE for the graviton operators. And then it has been mentioned in Laura's talk that the conformally soft limits nicely encodes all the soft limits in momentum space. So it's very natural to define this conformally soft operators with integer conformal dimensions. And then once we do this definition, we can do a mode expansion for each conformally soft operators. And then from the celestial OPEs, including all the contribution from the L minus 1 bar descendants, we get a closed algebra from the conformally solved operators. And then, as you have already seen in this morning's talk, once we do a very simple redefinition of the conformally solved operators, we end up getting a very simple algebras written in this form, which is the W1.3 algebras. The main difference, as Tim already emphasized, is that we have this range of P, which takes the value of integer and also half integer. So this is the main difference between the so-called Ham C2 and the W1 plus infinity algebra in the old literature. So these half integer modes are really the new things here. Okay, and also as Tim already mentioned, this W1.3 algebra is a very natural geometric interpretation of the space in terms of the Poisson structure. But for us, we want to see if there's if this nice algebra can get deformed into an algebra with a cosmological constant. So the basic motivation is that the experimental has told us that our universe has a positive value of the cosmological constant. And then if we think about a space-time with cosmological constants, the simplest one would be the de Sitter or anti-de Sitter. So just to remind you that the symmetry group of the DS4 is SO14, or for ADS4 is SO2, 3. So the very simple question we would like to ask is that, is there a simple deformations of the W1 plus D algebras that contains a sub-algebra generating these two global symmetry groups for these two space-time? And then, for those of you who are experts in ADS-CFT, you might wonder, there's no proper definition of scatter amplitudes in ADS or DS. So the best thing we can do so far is to look for something that looks like scatter amplitudes, or reduced to scatter amplitudes in flat space, in the flat space limits. So people have constructed the so-called ADS Virasoro-Shapiro amplitudes, where in the flat space limits, they recover the Virasoro-Shapiro amplitudes in flat space. And then they also can compute the curvature corrections to these amplitudes. And our idea is that to take a few theory limits of their results and then try to extract how the cosmological constant affect the collinear splittings for the amplitudes. So we naively take the few theory limits of their results. For the Virasoro-Shapiros, we get the usual tree-level 4-point amplitudes for gravitons. And then from their curvature corrections, we will get this kind of terms containing the cosmological constant. And then from these two terms, we can extract the corrections to the collinear splitting functions with the cosmological constant. And with these corrections, we can deduce how these corrections is going to affect the celestial graviton OPE in the presence of the cosmological constant, which takes this form. However, once we run the calculation as we have for the flat space, if we include these correction terms, it turns out that we don't really get a consistent algebras, including these corrections. The basic fact is that it doesn't satisfy the Jacobian identity. However, we can slightly modify the OPE coefficient, and also including terms that makes the OPE symmetric between 3 and 4 particles. And then once we've done that, we include all the, as we have in the flat space case, we include all the L minus 1 bar descendants. And it turns out that with this form of the celestial OPE in the presence of the cosmological constants, we run the same calculation as we had before by doing the mode expansions, we end up getting this algebras with the deformed term here. And then interestingly, once we do the redefinition as we have for the flat space case, we end up getting a very simple formulas given by this form. And then from here, we can check that it does satisfy the Jacobian identity. And moreover, this simple formula has a very interesting subalgebra. Remember, we want to make contact with the global group of the de Sitter or anti-de Sitter. So we identify the closed subalgebras for this algebras, which is associated with the modes with the integer and half integer, the first three integer and half integer modes for the algebras. And then you can show that this is a closed algebras, and with the simple identifications with basically rewriting this algebra in this way, we can rewrite it in this form, and some of you might recognize that this is very similar to a BMS algebra, except that we have a non-commuting p here. If we send the lambda to be 0, we get exactly the BMS algebra. And then once we have that form, we can easily identify how we can make connections with the symmetry group of de Sitter or anti-de Sitter. So we can just do some redefinition of the L and L bar generators, so that we can nicely organize the subalgebras into a form into this form, which is exactly the SO14 and SO2, 3 group, depending on the size of the cosmological constant. And moreover, it has been shown that this the simple algebra that we got can be obtained by using the twistor approach. So yeah, this, and you might heard of it from Giuseppe's talk about it. So to conclude, we constructed a cosmological deformation of the W1 plus infinity algebra in flat space. And the result is very simple, and also it depends on the size of the cosmological constants. We got the symmetry algebras of DS or ADS. And but as I said before, the naive field theory limits of the known results in the context of ADS CFTs doesn't really give us a consistent algebra. So maybe there's something missing in the field theory limits that we need to be care about to really understand a precise connection with other people's work. And also, one thing might be interesting is to look at how this W1 plus infinity algebra can be realized in the context of asymptotic symmetries of DS or IDs. So I will stop here.
Questions?
So I have two related questions regarding the subleading terms in the graviton OPE and their deformations. Mm-hmm. So usually from the collinear limit you only get the leading 1 over z term, right?
Yeah, exactly.
And if you would want to know the subleading terms, you would need to look at the subleading collinear terms, mm-hmm. which are not so simple. I mean, they don't factorize. So that's, I mean, to me it's a big problem, but your deformation is 1 over z squared.
Yeah, exactly.
And so it's competing with those subleading flat space corrections.
Yeah, you are right. So what we are doing is that we really taking the small lambda limits of it. So we sort of like consider the small lambda limits, which guarantee that this this z square term, 1 over z square term is still small compared to others. Yeah.
Okay.
But in Giuseppe and collaborators' paper, they show that in the certain sectors, this lambda correction is like all order. So we don't really need to stick to the very small lambda limits. Right? I'm not familiar with that.
Right. Yes, but I mean, to me, it's a bit strange to talk about deformations of the 1 over z squared, while you don't even know what is the leading 1 over z squared term. I mean, the non-corrected term. But okay.
Other questions? Maybe just pass it to the top and then we'll work our way across.
Hi. Sorry, I have a stupid question. So, in this celestial framework, the chiral algebra that you construct is codimension 2, while in the ADS framework you would expect like a codimension 1 algebra. So how do you count for that?
I think this has to do with the Carolian limits of ADS. Yeah, so in some sense you will see these infinite enhancements in the Carolian limits of the usual ADS symmetries.
Okay.
So let's go over there and then we'll come back for process.
Yeah, I just wanted to make a comment about the reverse direction. So there are some known sub-theorems for like de Sitter correlators. And then there is, at least in perturbation theory, there is a relation between de Sitter and amplitudes. If you go to special singularities of the cosmological correlators, you pick up the amplitude. So I think that it would be very, very interesting to see that, like, I don't know, if this W infinity algebra can be derived. So even in the flatter space limit of the correlator, I mean, if you go on the singularity to see like how these two algebras are related to each other.
Yeah, that's just an interesting point. Yeah.
All right, let's do the relay again to the process.
Yeah, I think it's a version of some of the previous questions. So we have an infinite extension of an algebra that contains the isometry of ADS4. This means you have an infinite extension of a conformal algebra in 3 dimensions. Is this a known extension? And what is that theory, that CFT that has such an extension?
Yeah, we don't know. We don't know.
Okay, well, with that, let's thank Ben for a very interesting talk.